Hi everyone, and welcome to this session on ALE Network Solution. Today we'll focus on SPB or MPLS for your mission critical network. I'm Sandra Rawalison, and I'm your webinar host for today's session, which will last about 45 minutes. So before we start, a few reminders. First, this webinar is currently being recorded. If that's an issue for you, we encourage you to disconnect now. And second of all, the presentation is available in the handout section now, so you can download it. And during this presentation, all your lines will be muted. We have in this webinar, Patricio Martello. Hi, Patricio.
Hello.
Solution Architect Director. So you can take the chance to ask or share any comments or questions around the solutions on the GoToWebinar control panel. Our team will take a few minutes at the end of the presentation to answer them. So Patricio, the floor is yours.
Thanks, Sandra, for the introduction. So hello everybody, and welcome to this session, SPB or MPLS, what to choose for your mission critical network. I've chosen to run this session for a couple of reasons. The first one is that I've seen some customers adopt MPLS and then regret it. But don't get me wrong, MPLS is a very successful technology that has been around for over 2 decades, and it is very widely adopted. And there's good reasons for that. We at Alcatel-Lucent Enterprise offer this technology currently through our partnership with Nokia, and we are also bringing MPLS support to our OmniSwitch product line towards the end of the year. So in no way I intend to criticize MPLS, but MPLS, with all its strengths, is not necessarily the best solution for every problem. So my first goal is to show how many of the use cases that you may think require MPLS can also be addressed through SPB. The second one is that I still see people compare SPB to spanning tree or trill. I think that comparison is outdated. It is no longer the relevant comparison to make, because that discussion has been settled a long time ago, and it's very easy. Firstly, have you ever heard anyone promoting the strengths of spanning tree? No, I did not think so. So that's an easy one for anyone who has experienced a network meltdown caused by spanning tree misconfiguration or failure. And if you know of any customer using trill, then please let me know. But more importantly, SPB can do far more than either of those two technologies. So making that kind of comparison with spanning tree or trill is a waste of time. The right comparison is SPB or MPLS. And if you want, you can add EVPN to the discussion also. But I will leave EVPN for another session. My third goal is showing you where SPB excels. I'm not hiding the fact that I am a big fan of SPB, and I do love this technology. I've even written the architecture guide on it. But in saying that, I will provide you factual and objective information to help you understand when SPB can be the right choice. And choice is the key word here, because if your only tool is a hammer, then every problem looks like a nail. So with that, here's the agenda for today. I start by giving you some examples of use cases that may call for MPLS or SPB and the reasons why. Then I'll go through some of the received ideas that are often presented as reasons to adopt MPLS, and I will explain why reality can be much more nuanced than that. After that, I will present a timeline of some of the most relevant technology milestones of the last 2 decades when it comes to networking to put these two technologies in perspective. I will introduce some of the most important aspects of SPB, and then I will close with key takeaways. So let's begin. What are the use cases and the main technical reasons why these two technologies are used today? If we look at it from a technology angle first, those reasons usually come down to, first, multi-tenancy, that is to say, a network that provides services to either multiple external or internal customers or organizations or user communities, and must keep those customers' traffic isolated from one another. The second one is segmentation of different traffic types. or user communities for security reasons. For example, segmenting IoT devices or creating different logical segments for contractors, for guest users, or services which are outsourced to third parties. Isolation refers not only to keeping those different customers or traffic logically isolated, but also isolating that traffic from the network core. And generally speaking, any customer that is already separating traffic or users in multiple VRFs, that is virtual routing and forwarding instances, is a good candidate for either of those technologies because configuring multiple VRFs and multiple routing instances hop by hop across multiple hops does not scale. That is not to say that with SPB or MPLS, you do not use multiple VRFs anymore. You still do, but those multiple VRFs only exist on the edge nodes and not on every intermediate node. So that's the techie part. But talking about customers or use cases, what are some examples? These are some examples that we see on the slide. And we have customers in all these verticals using MPLS, and we also have customers in all these segments using SPB. The first one is clearly service providers. If you are a service provider, you clearly tick all the boxes of multi-tenancy, etc. But it's not only service providers. There's also customers in higher education, in government, in transportation, such as metros, in utilities such as oil and gas or electrical, IoT use cases in general across all verticals, intelligent transportation, in the data center, video surveillance, and smart cities. All of these are examples of customers that require multi-tenancy, segmentation, isolation, multiple VRFs, and are currently using either of these two technologies. Let me illustrate some of these concepts. The first one is multi-tenancy and segmentation. There are two ways of looking at the same technical feature. What it means is slicing the network into multiple logically isolated segments for different customers, whether external or internal, different organizations, different user communities, or different applications, services, IoT devices that need to be segmented and isolated from one another, primarily for security reasons. These tenants or segments refer to layer 2, that is bridged, or layer 3, that is routed, VPNs, virtual private networks. The example on the slide is a campus example in which the network is sliced into a user VPN where we have our corporate users, another VPN for HVAC, that is heating, ventilation, and air conditioning, where we have devices such as thermostats and temperature controls and others, where the management of those devices may have been outsourced, and lastly, another VPN for access security with door locks and security cameras, which may be outsourced to yet another entity. MPLS is well known for its ability to create layer 2 and layer 3 VPNs, but what is less known is that SPB is also perfectly capable of delivering the same kind of service. The first area I want to touch upon is multi-tenancy. SPB makes it really easy to create layer 2 and layer 3 VPNs, which can represent different external or internal customers, or as we see in this example, services. One for end users, another one for HVAC, another one for access security services, devices. VPN services are delivered as an edge feature, which means that creating additional services or modifying existing ones requires no touch to core nodes. VPN traffic is tunneled through the core, and therefore the core is isolated from customer traffic as much as it is isolated from any changes to those VPN services. What's more, creating these VPN services does not require additional routing instances to manage. VPN services bring increased security without additional complexity. While VPNs keep customer traffic isolated, the second concept is core isolation. Whether we are talking about MPLS or SPB VPNs, those VPN services are different virtual logical planes, separate from the physical plane. The core is isolated from the VPN traffic because traffic is tunneled. It is also isolated from service configuration changes because services are delivered from the edge and traffic is simply tunneled across the core. So that is why on the light blue user traffic plane, the core nodes are transparent and they are drawn in dotted line because those services do not need to be configured on the core nodes, only on the edge nodes. So, for example, if a hacker attempted to discover or do a denial of service, etc., his traffic is still on the user plane and not on the infrastructure plane. In short, both SPB and MPLS create this core isolation. The core is isolated from any service configuration. For example, in MPLS, services are defined on provider edge, also known as label edge routers, but not on provider or label switch routers. Similarly, in SPB, services are defined on backbone edge nodes, but not on backbone core nodes. This means that once the network is deployed, there is very little touch required on core nodes. This is clearly an advantage from an operational standpoint. So the core can concentrate on doing what it does best, which is forwarding traffic as fast as possible. Second, the core is also protected from the customer traffic because customer traffic is running on a logically separate plane. Let's go through some of the most common arguments people give as reasons to choose MPLS. Some of these arguments are just wrong, others are not wrong, but they're only partially correct. Or there's very important caveats that we need to be aware of to avoid some common pitfalls, because reality is always more nuanced. So the first one is about QoS. And the legend goes that if you really care about QoS, then you must use MPLS. When we talk about QoS, what we are talking about is traffic classification, queuing, scheduling, policing, shaping. If you look at the MPLS header, there's only 3 bits for QoS. These are the 3 EXP bits. Compare that to a simple Ethernet frame. The COS, class of service field, has exactly 3 bits also. So there's no difference when it comes to classification. Next, you have queuing, scheduling, policing, shaping. The MPLS standard does not say anything about these mechanisms. These capabilities depend on the hardware and can be applied to MPLS, Ethernet, or another encapsulation such as Mac-in-Mac used by SPB. So any difference in classification, queuing, scheduling, policing, shaping is given by the hardware, not by the choice of protocol. Enabling MPLS will not magically add more queues or scheduling mechanisms, etc. The hardware capabilities of a big carrier-grade box, such as a Nokia service router, are obviously different from the hardware capabilities of an enterprise-grade box, such as an OmniSwitch. But it's not because of MPLS, it's the hardware that is different. So where did this come from? It probably originates from traffic engineering. With traffic engineering, we can manipulate paths and reserve bandwidth. However, traffic engineering is very complex. It requires setting up a mesh of traffic engineered tunnels, which is an extremely hard thing to do manually. You need to use an additional piece of software, a controller, to do it. But even then, it is not simple at all. And for that reason, traffic engineering is used a lot less than you may think in the real world, because often throwing more bandwidth at the problem is far easier and even more cost-effective than traffic engineering. The next one is that MPLS with fast reroute ensures no service impact on network failure events and that the network can recover very quickly, the famous 50 milliseconds convergence time. And well, this can be true in some situations, but not in general. And why is that? Firstly, for fast reroute, we need to have a pre-configured alternate path with sufficient bandwidth. If the failure only concerns that path and nothing else, okay, convergence can be fast. However, when looking at it from a service point of view, the failures can involve the customer edge or the provider edge nodes themselves. And the end-to-end convergence may require protocols such as VRRP, for example, or require convergence of the IP routing protocol level, such as OSPF. And that will generally not be anywhere near 50 milliseconds. And if we are talking about BGP, you should know that BGP does not provide the best convergence time. Let's remember that other protocols such as LAG or ERP can also achieve 50 milliseconds convergence time. So it is not as simple as that. We cannot generalize. There's important caveats, ifs, and buts. The next one is about security. While it is true that MPLS provides isolation between different VPNs and between those VPNs and the provider network, so does SPB. Neither MPLS nor SPB cover encryption. Traffic is unencrypted, at least by default. In both cases, we can encrypt the links using MACsec, for example. Talking about authentication, again, the MPLS standard says nothing about authentication either, nor does the SPB standard. However, SPB equipment is designed to authenticate users and devices before mapping them to the service and not simply mapping an interface or a VLAN to a service. Later, I will talk about the security benefits of SPB for microsegmentation and zero trust architectures. And the last one is about scalability. Of course, MPLS networks can scale. However, we need to be careful. Scaling takes much more than just MPLS. Again, for similar reasons as the QoS argument, MPLS will not change the size of the routing table or the number of ERFs that the hardware can support. Scalability depends on the protocol, but also on the hardware and on good design. For example, an MPLS VPN uses BGP. BGP requires a full mesh of peering, and for that reason, it does not scale unless you use rad reflectors. An SPB network also can scale to thousands of nodes, which is sufficient for most enterprise networks and even small service provider networks. So, okay, I will stop here because I think you get the idea. But these are arguments that are thrown around often and often without any more substance than what is written on the slide. So it's important to understand that there are caveats. MPLS goes back to the late 90s. It was originally Cisco's tag switching technology. So it is interesting to take a step back and think about what technology looked like back then and what happened after. Mobile phones, for instance, were capable of running a single application, voice calls. Well, that is not 100% true because there was WAP, but who used WAP anyway? Computers connected to the network using an Ethernet cable at the office and a phone cable when at home or on the go. And that required a modem which made that weird noise when setting up the call to the ISP. Servers did not move unless you put wheels on them. And enterprise WAN connectivity was still using virtual circuits in a hub and spoke topology. Still, for the most part, the older and slower frame relay, or to a lesser extent, the newer and faster ATM. But ATM was still a complex, slow, and very expensive technology. It was designed to carry different types of traffic, including voice, and as a result, many compromises were made. One of which is that it used small and fixed 53-byte cells with only 48 bytes of payload. And that complicated carrying IP packets with a variable size. So there were different attempts to run IP over ATM, and none of these attempts was particularly successful. Carrying layer 2 traffic was even more complex because ATM had not been designed for broadcast communication. LAN emulation was an awfully complex technology that never took off. ATM was also a circuit switching technology, and for this reason, it led to hub and spoke designs instead of mesh peer-to-peer designs. ATM VPN services required BGP on all nodes, including the core nodes. So it is in this context that MPLS comes and addresses these weaknesses in ATM. Carrying IP or Ethernet services became simpler. VPN services no longer required BGP on core nodes. It was well suited to peer-to-peer communications and not just hub and spoke. Layer 3 VPN services were the killer app for MPLS, and it really took off. It was a great success. However, many things have changed since MPLS was standardized in 1999 with RFC 2547. For example, it was not until 2 years later that VMware introduced the ESX hypervisor, and 2 years after that they launched vCenter, and with vCenter, vMotion. So that is VM mobility. Desktop mobility only really started to happen with the 802.11g standard and the wireless LAN controllers around 2003, because before that, with the 802.11b standard, it was not really suitable for enterprise mobility. It was primarily used for home and for meeting rooms. It was not until 2007 that the first smart mobile devices were created, the iPhone. IoT really took off a bit later in 2008 when we reached more than 1 billion IoT devices. In 2010, the iPad came out, and with that, mobility accelerated and BYOD became a thing. Zero trust architectures were also defined for the first time in 2010, and the SPB standard came another 2 years after that in 2012. And it was only 5 years after IoT became a thing that ransomware also became a thing, and the first expression of ransomware, which is the CryptoLocker. So the MPLS standard precedes these trends. Now, that does not mean that an MPLS network cannot cater to these trends, but SPB implementations such as the one we have on the OmniSwitch have been designed from the get-go to adapt to users, devices, and virtual machines that move, that are not static. And for this reason, they are extremely well suited to micro-segmented and zero trust architectures in these very dynamic environments in which perimeter-based security is obsolete. So let me elaborate on that. SPB is seamlessly integrated with the network admission control framework, and what this means is that users and devices can be authenticated and automatically mapped to their corresponding VPN service based on their identity, and in addition to that, they receive a set of policies that further control what they have access to, as well as QoS policies. And that is to say that with SPB and the network admission control capabilities, which are built into the network devices, we achieve software-defined macro and micro segmentation. And this is key because, as I explained before, with mobility and IoT, neither users nor devices are static. They're mobile. They connect, they disconnect, they move, and they connect again. So zero trust and micro segmentation cannot be done statically. It has to be dynamic or software defined, because otherwise it would become unmanageable. So the combination of user device identity, day or time, the location, and the device fingerprint determine, on the one hand, the VPN, that is the service that the device is mapped to, and on the other hand, so that we refer to that as macro segmentation. And on the other hand, they determine a set of security and QoS rules that will be applicable to that device. And that is the micro-segmentation part. How does this seamless integration between network admission control and SPB exactly work? So let me illustrate it. Let's say we have a network node. We have enabled authentication on all ports. So a user comes in, the user connects, and presents a certificate as proof of identity. If this is the first user to connect on this network node, the user VPN will be automatically instantiated on the switch thanks to the SPB control plane. Similarly, if we connect a camera which authenticates through its certificate or its MAC address, for example, the access security VPN is instantiated and the camera is mapped to it. And the same thing happens when we connect a temperature sensor, for example. 802.1x using certificates is the most secure case, but the authentication scheme is flexible enough to accommodate other authentication mechanisms or even classification rules based on IoT device fingerprints, etc. And each time a device is mapped to its VPN services or service, it receives a list of additional security and QoS policies. The same thing happens when the device disconnects. The VPN service is deprovisioned from the switch. The bottom line is that with SPB, you can easily create virtual software-defined segments for different user communities or IoT device types and adopt a zero-trust architecture. This is because in SPB, like in MPLS also, services, VRFs, etc., are only defined at the edge and not on every node along the path. But on top of that, SPB is natively integrated with network admission control such that the mapping of a user or a device to a VPN is automatic. It is dynamic and it's based on authentication and not static port or VLAN mappings. And just like the mapping of user or device to a VPN is dynamic, the mapping of security policies is dynamic and software defined too. Having services that are only defined at the edge and not on core nodes drastically simplifies the deployment and maintenance of VPN services compared to other approaches such as pure VRF Lite, which require configuration on all intermediate nodes. But on top of that, the SPB control plane is beautifully simple as it relies on a single control plane protocol and not a stack of protocols. Because the MPLS control plane is more complex and heavier, this results in more complex deployment, troubleshooting, longer training and certification requirements than when using SPB. Because MPLS uses a stack of protocols and every protocol in the stack has a dependency on the ones below. So let's compare the control plane between these two technologies. We start with Ethernet as the base. In MPLS, we need an interior gateway protocol to build a topology and to have node reachability in the backbone. For that, we can choose either OSPF or ISIS. One of them is enough. We don't need both. Then, with the route tables built by that interior gateway protocol, we need a way of assigning labels to traffic. For that, we use either LDP, label distribution protocol, or RSVP TE, or segment routing. But that only gives you a topology and labels. You do not have VPN services yet, so you need some more protocols. If we are talking about layer 2 services, you either need targeted LDP, which in fact means creating a full mesh of pseudo wires either manually or through a network management system, or the better way, which is based on BGP and is described in RFC 4761. But if we are talking about layer 3 services, then it is BGP, what is described in RFC 4364. Now, if we compare that to SPB, SPB uses a single protocol to do it all. That is ISIS. ISIS builds the topology table, it builds layer 2 VPN and layer 3 VPN services, and the same protocol is used to build the service table. So ISIS plays the roles of OSPF, LDP, and BGP all combined. But on top of that, ALE's IFAB has added additional automation and simplification such that the SPB backbone is automatically configured. The services are automatically configured, and users and devices are automatically mapped to the service that they belong to after they authenticate to the network using 802.1x, for example, because SPB, as I was saying before, is directly integrated with the network admission control plane. And in doing that, users and devices also receive a set of security rules according to their profile. So that is dynamic macro and micro segmentation. The bottom line is that using a single control plane protocol is clearly simple to deploy, but it is also simpler to maintain. There are no complex protocol dependencies or interactions to troubleshoot in case of problems. When there is a topology change, there is only one protocol that needs to converge, as opposed to what happens when using a stack of protocols, in which the upper protocol cannot converge until the protocol below has converged. So in short, a solution based on a single control plane protocol is definitely simpler to learn, simpler to deploy, and simpler to maintain and to troubleshoot than one that is based on multiple stacked protocols. As an IEEE standard, SPB not only interoperates with other vendors' SPB implementation, but it is also backwards compatible and interoperates with other protocols. What this means is that SPB adoption does not require a forklift upgrade. At layer 2, interoperability. At layer 2, SPB interoperates with all previous IEEE standards such as 802.1q, QNQ, or LACP. Therefore, an SPB migration can start at the aggregation and core layers, while the access layer can wait until the next refresh cycle. At layer 3, routing in and out towards external non-SPB networks can use standard protocols such as OSPF, ISIS, or BGP. And this is also valid for multicast traffic, which can interoperate through protocol-independent multicast and its different variants. So bottom line is SPB can interoperate at layer 2, layer 3, and not just unicast, but also multicast traffic. And the benefit is investment protection. There is no need for a big bang forklift upgrade because the migration can be performed in phases and aligned with refresh cycles. Another thing to know about SPB is that it's an all-in-one Swiss knife solution. What do we mean by that? It means that you can tackle different problems with it. You can use it in the campus, and in fact, SPB was first conceived as a replacement for spanning tree. So SPB was originally, as I said before, conceived as a replacement for spanning tree. Spanning tree is an ancient protocol designed to prevent loops. However, it is a real source of headaches because a misconfiguration or errors in spanning tree can result in a complete meltdown. And on top of that, it is very inefficient and wastes network capacity, resulting in poor performance. So SPB came to fix all that with a modern protocol that makes networks stable and performant. But it's not just the replacement of spanning tree. It adds, as I was saying before, multi-tenancy with layer 2 and layer 3 PNs, and that makes it ideal for microsegmentation and for IoT in particular. The second area is the data center. You can use SPB to build data center fabrics spanning one or multiple sites. These fabrics provide any-to-any connectivity over optimal low latency paths, making it ideal for modern virtualized or private cloud environments. The third one is the WAN. SPB offers layer 2 and layer 3 VPN services similar to MPLS services, yet much simpler to deploy and operate. And these services can deliver multi-tenanted services to multiple sites connected across the WAN. The fact that you can address all three problems with one solution is quite unique to SPB. Instead of having three different solutions, such as spanning tree in the campus, VXLAN overlays in the data center, and MPLS in the WAN, you can do all three with one protocol. And this reduces complexity of managing multiple dissimilar technologies. What also enables the use of a single solution for multiple problems is having consistent support of this protocol and related features across all the required product lines. If you compare that with other technologies such as MPLS, but also VPN, they are not so broadly supported, and for that reason, they can be a good solution for the WAN or for the data center, perhaps for the campus, but rarely for all three. But with SPB, we have broad support across multiple product lines with the same operating system and consistent feature set. On modular switches with high density and capacity that you can use at core, aggregation, or access layer, on compact switches that you can use as a topo rack in the data center or in a span and leaf architecture, but you can also use as a compact core in the campus. And these switches also provide high capacity wire rate performance in a compact form factor. At the access layer on the advanced access switches that can also be used as a small core, offering multi-gigabit performance and HPOE while supporting a broad range of access layer security features. And even on environmentally hardened switches for harsh environments, which with an extended temperature range for challenging EMC, EMI, while still offering HPOE and supporting the same range of features. Finally, it is also supported on the OmniVista NMS to visualize topology, the paths, and to configure SPB services through a friendly GUI. Bottom line is that not only SPB is suitable for using campus, data center, and WAN, but it is broadly supported across the board with a consistent feature set and same operating system. And you cannot say the same about other technologies such as SPB, that SPB is sometimes compared to, such as MPLS or EVPN, because support of those technologies may be limited to specific families that are more suited to the WAN or the data center, maybe the campus, but rarely all three. I can definitely go on and on, but I'll stop here and let me close with some key takeaways. SPB comes with service provider capabilities which are similar to those of MPLS. It provides multi-tenancy, it isolates the core from the customer's traffic, and it improves scalability and convergence time compared to other alternatives such as layer 3 routing and VRF. SPB also, sorry, I have a problem with the animation. SPB also is an ideal technology for implementing a zero trust architecture based on microsegmentation because it integrates seamlessly with network admission control and the software-defined microsegmentation capabilities, such that users or devices can be authenticated and mapped to their VPN based on their identities, and that layer 7 deep packet inspection rules can be dynamically applied to them on the fly. The third point is that these additional capabilities do not come with increased complexity, quite the opposite actually. And this is because it can all be achieved with a single control plane protocol, which results in quicker deployment and simpler troubleshooting. And this same solution is applicable to the LAN, to the WAN, and the data center, bringing further simplification compared to using different solutions in each of those blocks. And before jumping to the Q&A, I want to leave you with the link to our Spacewalkers Live Community Tech Days, where you can find many in-depth technical sessions and demonstration, including an in-depth hands-on workshop on SPB that will be out within a couple of weeks. So make sure you check it out. So with that, it's time for Q&A. So I will open the Q&A panel. Okay, I see we have several questions. We have a few minutes left. First question is if it makes sense to use MPLS if we are already talking about SD-WAN. Well, it's an interesting question. And there's a follow-up question, what about SD-WAN? It's an interesting question, SD-WAN. SD-WAN does not directly compare to SPB in the sense that so SD-WAN is an overlay mostly intended to run over internet links, whereas SPB, while it can do that, it's mainly intended to run over, let's say, dark fiber or own links. There's another question about MPLS, whether it will be written in the data sheet. Well, it will be written. I assume the question is about support on the OmniSwitch product line. It will be written in the data sheet when it is released. Interesting to see another question on how it's different from SD-WAN and SPB. Well, as I said before, SD-WAN is a technology which is intended to run as an overlay primarily on top of internet links to decrease the cost, whilst SPB can do that, but it's not really intended for that. Another question, where is the security enforcement point? Does it work with ACLs? Let me see the rest of the question. Or stateful firewalling. So the enforcement point is at the switch port. And depending on the product, it will use ACLs or stateful policies, which I'm not going to call firewall policies. But on some products, such as the 6860E and 6860N, we support DPI policies, which are stateful. And those policies are application policies, so layer 7. And we can detect thousands of different applications and apply stateful policies to those applications. But I'm not going to call them firewall policies, but they're definitely layer 7 DPI policies. So it's a combination of both. And depending on the family, we can use ACLs or those DPI policies. There's another question, which is, with ISIS being used as the main protocol in SPB, do all routers have to be designated in both layer 1 and layer 2 areas? Quite a technical question. So all bridges using SPB run the ISIS protocol. They use layer 1, not layer 1, but L1 adjacencies. However, SPB can be overlaid over other networks that do not use the SPB. For example, SPB can be overlaid over layer 2 networks that use a different type of technology, for instance, Q&Q, VLAN stacking, or even VPLS, even microwave bridging. And it can also be overlaid on top of layer 3 networks when combined with VXLAN. So that is the last question I see on the panel. I don't know if there's anything else, Sandra.
No, that's all that I see as well. Thank you, Patricio, for this presentation. Very interesting.
Okay,
and,
thanks.
Sorry for the little poll.
Okay, thanks.
Thank you, everyone, for attending this webinar. And
thanks,
yeah.
everyone, for your attention, and see you next time.
See you. Bye.
Bye-bye.